Welcome to our webinar Basics of Protection. These sessions are made for those who start working or who are new in the field of protection and where a solid understanding of relay protection for distribution and transmission grids is essential. My name is Gerd Einsiedler and I'm happy to guide you through this session of the webinar. Some of you might already know me. I have been working in protection and automation for nearly 30 years. Since September 2023, I am part of Siemens Power Academy in Nuremberg as a certified trainer for protection. And today I'm introducing you to the basics of protection lectures. How do we build a protection scheme part 1? Reliability in protection, a difficult discussion. How do we build a protection scheme part 2? And since we receive a question rather often, yes, we will record the webinar and make the recordings and the slides available to all registered participants. If you already joined one of our last webinars, you already know the Q&A field in this application. Please type in your questions to the presenter in the question field. We will answer your questions during the dedicated Q&A session after the series on 21st of June. In addition to me reading aloud your questions, you could also chat with your experts in the background. Please be aware of the following limitation. The chat is available in live mode only. Q&A questions will be answered via email if not managed during the live session. And just in case you are in full screen mode, press Escape to see the Q&A and chat box. And now let me introduce our expert, Prof.Dr. Lemmer. Siegfried Lemmer graduated and received his PhD at RWTH Aachen University. He joined Siemens in 1986. For many years, he was head of the product lifecycle management for protection, where he was deeply involved in the design of CPROTEC 4 and CPROTEC 5 relay families. Within a master course of power engineering at Brandenburg University of Technology, Cottbus-Senftenberg, he presented lectures about protection for nearly 2 decades. In 2016, he retired from Siemens, but continued his university lectures. Siegfried, and now we are curious to learn more about the basics of protection technology. The stage is yours.
In the previous chapter, we had a look at the different aspects of protection, at the protection principles, and in this chapter I will describe how we build up a complete protection scheme based on these considerations. And we will do that in 4 different steps. First is the selection of the main protection, of the short circuit protection. Then we look at the selection of additional protection functions. Third one is additional functions, which are not really protection functions. And then the last chapter will refer to redundancy and reliability. And I will squeeze in a separate chapter on that. For that reason, this chapter on designing a protection scheme is separated into 2 parts. The first part consists of steps 1, 2, 3. Then I will squeeze in a chapter on reliability, and then we will have a look at this redundancy topic, and I will show a couple of examples. So let's start with the first thing, select the main protection, the short circuit protection. And in order to explain that, I would like to show this diagram. You see here the different areas of application. On the horizontal axis, you see the voltage levels, starting from medium voltage via high voltage levels to extra high voltage, or you can say from the distribution via subtransmission to the transmission level. And on the vertical axis, you see the different components. From the top down, it would be long overhead lines, then cables and short lines, transformers and bus bars. And then I indicate in this diagram what is a typical main protection function in this area. So let's start from the top, from the long overhead lines. You won't normally find them in medium voltage, so you find them in high and extra high voltage application. And in this area, the distance protection is in many cases the main application. You can say nearly on all high or extra high voltage overhead line in the world you find a distance relay. But there is also some overlap with line differential protection, especially if you come one level down to the cables and short lines. You find more line differential protection, or you find both, because I indicate in this diagram with this yellow area there, in the field of extra high voltage line protection, you have typically a duplication of protection. That means there you have either two distance protection relays installed or a distance relay and a line differential relay. If we come to cables and short lines and look at the lower voltage levels, at the medium voltage level, then we have the main area of application for overcurrent protection. Again, also with a certain overlap with line differential, depending on the length and on the situation you have there. So you see, it's not an exact definition. If you have this type, you need this type of protection. It depends a little bit on the application. If we look into transformers, on the lower voltage levels, we typically have overcurrent protection or just fuses as protection. If we come to the higher voltage level, the typical main protection against short circuits is the transformer differential protection. And the lowest level here, in this case, the bus bar protection. Bus bars are very important components, so they typically get, especially in the higher voltage levels or in important distribution substations, they get a separate protection only looking at the bus bar. And there the typical protection function is the bus bar differential. If we look at simpler distribution substations, there we need more economic solutions. And one typical application there is the so-called reverse interlocking. That is a special scheme where the overcurrent protection relays, which are available there anyhow to protect the feeders, are connected in an interesting way to protect the bus bar with very short tripping times. So that was the selection of the main protection function. And let's now come to the additional protection functions. You may know in digital protection relays, we have the possibility to activate a lot of more functions. In old times, you had to install separate relays for all the additional functions. In digital protection relays, you have them all together. And what I can do here is I can just explain a selection of additional protection functions which are possible. It always depends on the type of equipment, on the voltage level, and also on the common practice in the company you are working in. And it depends also on sometimes on the country where you are working in, the common practice in the country. The first class of additional protection functions I'd like to mention is the earth fault protection. And in this context, we have to distinguish between two different cases. If we have a system where the star points of the transformers are grounded, then the question is, do we need special functions because the overcurrent protection or the distance protection have some sensitivity limits? They cannot catch high resistive faults. And in some areas, it may be necessary to install separate protection functions to detect high resistive faults which cannot be detected by the main protection functions. And these are earth fault protection functions in systems with grounded star points. On the other hand, if we have a system where the star points are not grounded, or where we have a Peterson coil installed in the star points, then earth faults are no short circuit. That means our short circuit protection we selected in the first stage does not react at all on any earth faults. That means in this case, we need in any case dedicated earth fault functions to detect these type of faults. The good thing here is in these systems we can continue operation because earth faults are no short circuits, but nevertheless we have to detect these faults and we need protection functions. For that, we will have a separate webinar on this topic. That means how to detect earth faults in systems where the star points are not effectively grounded. The next point is overload protection. Where is overload protection required? It's mainly for transformers, for motors, and for cables. And the overload protection is basically a thermal protection. It's a protection against too high temperatures. And in the simplest approach, you have a thermal model in the protection relay. You measure the current, because you need the current measurement anyhow for the protection function. And you feed in the measured current into a thermal model of the transformer, of the motor, of the cable, and try to calculate the temperature of the transformer or the cable or the motor. And if you find out a certain maximum temperature could be exceeded, you trip the device. Of course, this is not an exact procedure because, for instance, you don't know the ambient temperature, you don't know the cooling factors and so on. That means you have to do a lot of assumption. If you want to make it more precise, you can also install temperature sensors, for instance, in the transformer and feed that into the protection so you get a more precise estimation of the temperature, and even you can install these things in expected hotspots. And that means you can go closer to the limit. If you don't do any temperature measurement, you have to design the thermal model in a way that you are on the safe side. If you do temperature measurement, you can go closer to the limits. It's important to distinguish between overload protection and short circuit protection. You will see both protection functions have some inverse time curves, but if we talk about overload protection, we typically have much longer tripping times there, as these thermal effects are pretty slow effects. That was overload protection. Another thing I'd like to mention here is the so-called arc protection. We will see that schemes with overcurrent protection tend to have pretty long tripping times for short circuits in the infeeding substations. That means if you have an arc fault in the infeeding substation, the fault duration may be pretty long. And to avoid that, you can add a so-called arc protection, that is a protection function which is based on an optical detection of an arc. That means if you have an indoor substation and you have an arc in the switchgear, it's of course very bright in the switchgear, and this can be detected and can be combined with the current flow, and then you can speed up the protection and can reduce the duration of the short circuit. Of course, you need additional equipment, you need optical sensors, and you need devices who have measurement inputs for these sensors. Breaker failure protection would also be an additional protection function. What is breaker failure protection? Breaker failure protection is a function which detects a situation where a protection relay has detected a short circuit, gives a trip command, but the breaker doesn't work. And this function consists of two parts. The first one is very simple, to detect the breaker failure. You can imagine the protection relay gives a trip command, it sees a short circuit, and nothing happens. And it's easy to detect that because the protection relay sees still current flow, although it has issued a trip command. That means the detection of this situation is normally pretty easy. But then the question is, what are we going to do in such a case? Sometimes it's a possibility to do a retrip on a second coil of the circuit breaker. But if that is not possible, or if that doesn't work, you have to trip all other circuit breakers around the bus bar. That means you need, after you have detected that situation, a wiring that gives a signal to all other circuit breakers. And you can imagine if you do that for all protection relays, it ends up in a pretty complex wiring. And for that reason, if you have a busbar protection installed there, the busbar protection needs this wiring anyhow. And for that reason, you often have the breaker failure protection included as a bifunction in the busbar protection and not in the feeder protection. Another thing I'd like to mention is the power swing detection function. That is a thing which is important in transmission systems. In transmission systems, especially if you have large systems or if you have weak systems, you may have situations where different areas of your network start somehow with oscillations. That means that the phase angles start oscillating a little bit. And that can lead to strong power flows. These are not short circuits, but that can lead to strong power flows. And these strong power flows can be interpreted as short circuit by the distance protection, for instance. And normally this has to be avoided. That means one application of the power swing detection function is to detect such a power swing and to tell the distance protection, stop, don't react on that, that is a power swing, that is not a short circuit. That means the power swing detection functions are sometimes used to block the distance protection. Another application is, and you can imagine that requires intensive studies of the network, another application is if you detect such power swings that you cut the network at dedicated locations. That means you can also use this power swing detection function to trip the circuit breaker in order to stop these oscillations. And finally, I would like to mention a number of other small protection functions we also sometimes need. Voltage-related functions, or for motors we have some load jam or unbalanced load. Load jam can be, for instance, you have a locked rotor in a motor. Unbalanced load means you have suddenly interruption in one phase. And the last thing I mentioned here is frequency protection. That is often used for load shedding, for instance. Remember, the frequency you have in your system is an indication if generation and load are balanced. If generation and load are balanced, you have a frequency near your nominal frequency of 50 or 60 Hertz. If the frequency goes down, it's an indication that some generation is missing and you have to inject more generation into your network. But you can have critical situation where you suddenly lose a lot of generation because a big power station fails or the network is separated then. And then the frequency goes down very rapidly. And then the only situation to save the system is to cut loads, to come back to a balanced situation with generation and load. And this is done with so-called load shedding functions, and they depend on the frequency. That means you have different set points. If the frequency goes below 49.5 or 49 Hertz, you just switch off parts of the city or part of your loads to save the system to come back to a stable situation again, and then you have to try to reconnect that. That's normally done just with a frequency protection function, sometimes also with a df by dt function. That means that is a function which reacts on the rate of change of the frequency. So that was a selection of the additional protection functions you may need. And then in addition to that, we have a number of other functions which are not really protection functions, but which are also typically part of a protection scheme. And the first one I would like to mention is the auto-recloser. What is the auto-recloser? The auto-recloser is a function which automatically recloses the breaker after it has been tripped for a short circuit. Why does that make sense? Important thing is it makes only sense in overhead lines. In overhead lines, you have often the situation that, for instance, resulting from a lightning stroke in a thunderstorm, you start a lightning arc between a conductor and the tower. Then you have a situation where you have a short circuit current flowing in this lightning arc, high current flowing there. That keeps the air around this arc hot and ionized, and the current remains flowing, although nothing is really damaged up to now. If you then trip this current flow, the current stops, the air cools down, is no longer ionized, and if you then reconnect the breaker, the system remains in operation. So that's a scheme which is very often used on overhead lines. Important thing, it works only on overhead lines. If you have a fault in a transformer, the chance that you clear this fault by just tripping it and reclosing the breaker is pretty low, also in a cable. So it doesn't make sense. It only gives additional stress to the device. For that reason, it's only applied in overhead lines. And there you can go even one step further. The majority of all the faults are single phase to ground faults. And to clear a single phase to ground fault, it is sufficient to open just one phase of the breaker on both sides of the line. That means instead of opening all three phases on both sides of the affected line, you open only one pole and the other two phases remain connected. And it has significant advantages for this network that part of the line remains in operation during this interruption phase. The point is, if you want to do that, there are two preconditions. On one hand, you need a protection relay which has 3 different trip contacts, 1 per phase, and you also need a circuit breaker who is able to do that, who is able to trip single pole. And based on what you have on the circuit breaker side, there are different concepts in use. In many cases, this auto-reclosing function is only initiated in case of single phase to ground faults, which is the majority of all faults, and is then done single phase. If you have circuit breakers who are not able to do that, you have to trip 3-pole. But there are also concepts in use where you also do auto-reclose in case of multi-phase faults. That means depending on the type of fault, you do either a single pole trip or a 3-pole trip. So you see that makes the function a bit complicated. There are different concepts in operation depending on type of breaker, on the type of system you have, and the function has to be adaptable to these different concepts. That was auto-reclosing. Then you often have a lot of measurement and control functions available, and that depends on your control concept of the substation. You see, our protection relays do measurement anyhow to do the protection functions, and of course we can also use these measurements and send them via communication to a control center. We also can send any signals up, and we can even receive commands from the control center. If the control center, for instance, wants to trip a line, for instance, to do maintenance, we can do that through the protection relay without installing separate equipment for control. And that depends now on the control concept, what amount of functionality is used there. It is typically available in our relay. What is also sometimes there is the so-called interlocking logic. What is that? If you make use of these control functions, the protection relay can not only open and close the circuit breaker, it can also control isolators. For instance, the earthing switch, the line side isolator, the busbar side isolator, all that can be connected to the protection relay. It's not a protection function then, but it can be connected there, and we can do control through the protection relay. And there it is state of the art to have some logic to avoid wrong tripping actions. Just a simple example. You have an earthing switch there. If you want to do maintenance on a line, you open the circuit breaker on both sides, and then you close the earthing switch because you have to earth the line to do maintenance there. But what you have to avoid is that somebody, just by mistake, closes the earthing switch while the line is still in operation, because that ends up in a short circuit. And that is the point where the interlocking logic comes in. That means if somebody gives such a command by mistake, the interlocking logic will block this type of command, because the interlocking logic says the circuit breaker is closed, the line is energized, it's forbidden to close the earthing switch now. So that's one example for interlocking logic. There are a couple of other switching actions which also have to be avoided. That was the field of measurement and control. Another bifunction which is often used is a so-called fault locator. Remember, the principle of the distance protection is we measure the impedance from the relay to the fault, and by that we know more or less precisely where the fault is. We use that to decide, is the fault on the line or is it on the next line? But we can also use it to give this information to the control center. For instance, if you have a 100-kilometer line and after a permanent fault where the auto-reclose doesn't help, you must look at the line, you must look what has really happened there. And if you have a long line, it makes some sense to ask the fault locator, what is your estimation where the fault is? Is it at kilometer 10 or is it at kilometer 80? And this is also a little bit a bifunction of the distance protection. In our relays, we use separate algorithms for that, because the algorithms used for the protection functions are designed for high speed. They must be pretty fast. And once a protection relay has issued a trip, it takes some time until the breaker opens. And in this time, we can still do measurement. We can do measurement with longer data windows, so we get a more precise measurement of the location of the fault, and this result is then given to the control center by the fault locator. So it's a typical function by function of distance protection. In overcurrent protection, it is only available if you have the voltage. Because remember, to measure the impedance, you need the voltage and the current. That means if you have a pure overcurrent relay or a pure line differential relay, you cannot measure the impedance, and then you cannot have a fault locator there. Synchro check is also a bifunction which is often used. That is required if somehow the system is separated, you have two parts and you want to reconnect them, and there you may end up in a situation that before you reconnect it, you have really different phase angles or different voltage amplitudes on both sides. And if you have such a situation that, for instance, you have a significant phase angle difference between the voltages, and you then close the breaker, you may get heavy transients, which may end up in an operation of another protection. And for that reason, you often use a synchro check function. That means this function measures or compares the voltage on both sides of the breaker and will only allow the closing of the circuit breaker if the difference between the voltages on both sides in terms of magnitude and in terms of angle is under a certain setting value. That is the synchro check function. Then we need sometimes so-called teleprotection logic. That is a logic which is used together with distance protection. That is a bifunction to distance protection to speed up the tripping time a bit. It can also be used for some earth fault functions, also to speed up the tripping time and to get additional selectivity. And the last thing I would like to mention here is a relatively new issue. You find it since decades in many papers, but the area of application is growing. It's the so-called synchrophasor measurement. What is that? That is a measurement of currents and voltages, but very precisely with phase angle and magnitude and a timestamp. That means in this case, you need a GPS synchronization in the device. That means you need any access to GPS to provide these exact timestamps, and you do then regular measurement of voltage and currents with a timestamp and send this data to a data concentrator. And if you do that, you are able to monitor transient situations in a system, like these type of power swings I mentioned on the previous slide. They are not visible in the normal operation of the control center. The control center does also voltage measurements, but on a very slow base. You can also only see steady state things there. Here you are really able to measure transients, power swings, and that can be used to get a better understanding of the system, to analyze what has happened in critical situation. And you can go even one step further. You can define, if you detect special situations where you are at the limit of stability, you can initiate some actions, splitting the system or whatever. So that is a new field where the protection function, or where the functionality is not completely in the device. The device is used as a measurement sensor for this function, and the function itself is on a central level in this data concentrator. So that was a look at the additional functions. Of course, it's not a complete list. There are other possibilities. It always depends on the application we have. Now we are through 3 of the 4 steps. And the last step is to look at redundancy and backup concepts. And my personal experience is that discussions about redundancy, reliability of the whole system are very difficult discussions. Because sometimes your stomach feeling on problems lead you into the wrong direction. For that reason, I would like to stop this part here and squeeze in a chapter where I discuss a little bit about reliability issues in protection. That will be the next chapter. And then after that, I will come back to this point. Let's talk a bit about reliability issues in protection. And I would like to start with just 3 statements on this topic. On one side, we should have in mind, if something goes wrong in protection, it may have severe impact. It can result in blackouts. So you as a protection engineer may become famous because the whole city is dark. It can also result in damage of equipment. It can result in injured people or whatever. That means the technology we are dealing with here is not a gaming thing. It is a thing where we have to pay severe attention that it really works. But we also know we cannot reach 100% reliability. That means whatever we do, there is a certain risk that the system doesn't work as desired. And this risk is accepted in all other areas as well as in protection. But we must do our best to minimize this risk, of course. We must do our best, but we must also have in mind we have economical constraints. We cannot do as much investment as we would like to do to optimize the system. We always have economical constraints. That means the amount of equipment we are allowed to install depends on, and also the manpower we have available depends on the voltage level and also on other quantities. You can imagine if you want to do protection for a simple distribution feeder, this has to be cheaper than the investment to protect a 400 kilovolt transmission line. That means there are also economical constraints. And in this framework, you have to define solutions, and state-of-the-art solutions have been developed in the companies. They are sometimes different in the different companies, also in the different countries. That means different ways of doing things are established, but they also all have these considerations in the background. So that is one introductional remark. Now I would look a little bit into some theoretical considerations. You often hear about things like mean time between failures, mean time to repair, outage rates, and so on. What is that in this context? Often we assume a simple two-stage model to describe an electronic component. That means you say you have an electronic device, it's either in operation or it has a failure. And you can draw a diagram like this. That means the device is in operation. After some time it fails, then it's repaired or replaced, then it's in operation again, and it fails. Of course, these time slots for the operational time should be a bit longer than indicated here in this diagram. But that type of model is often used to describe stochastic outages. And that is the important thing with that. These definitions which are used to describe the behavior and to describe the reliability of an electronic device, they are designed for stochastic outages of devices. We sometimes mention, for instance, the outage frequency. That means how many outages do you have per year, or does a component in an average have per year or per 100 years? That is so the outage frequency. Imagine, for instance, if you have an outage frequency of 1 outage per 100 years, that would mean if we have 100 devices in operation, 1 is expected to fail within 1 year. But you must have in mind it's only an average figure. It can also be 2 or it can be 0. The outage can be tomorrow or it can be at the end of the year. So these outage frequency are stochastic quantities. They are the more precise, the bigger the quantity of devices you have. Outage frequencies of industrial electronic equipment are typically in the range of 0.1%. That means you have typically an outage every 1,000 years, or you can say if you have 1,000 relays in operation or 1,000 devices in operation, you can expect 1 stochastic outage. The next quantity, which is also often mentioned, is the so-called MTBF, that is called mean time between failures. That is just the average time if a device is in operation. How long will it take as an average until it fails again? And that should be a thing which is pretty long. You can calculate that. There are defined methods to calculate that. I personally think that these calculations are not really relevant for our field of application, for our protection field. I will explain the reason later, but that term is sometimes used. Another thing is the mean time to repair. How long does it take to repair or to replace a device? And then you have the so-called availability. That is a figure which is typically something like 99.9%. That is the percentage of the time where the device is in operation. So these quantities are defined for simple electronic devices which can either be in operation or defective. But reality in protection is a bit more complex. One thing is the question, what is a failure? If a relay just fails, the good thing with digital relays is if they fail, they will alarm. That means the control center knows there is something wrong in the relay, protection doesn't work, you can, or you have to take the line out of operation, you replace it, and it goes. The problem is if the relay is dead, it has a failure, you don't realize it because, for instance, the wiring is broken to the circuit breaker. You may have a missing trip. That means you have a short circuit, the relay does not trip because of a failure. That type of failure is called missing trip, but we have another type of failure, and that is called unwanted trip. Theoretically, it's possible that a protection relay gives a trip command, although there is no fault on a trip. That means we can fail in 2 different directions, missing trip or unwanted trip. Both are things we don't like. So that means already that this simple 2-stage diagram in operation and failure is a simplification which doesn't really fit to protection. And there is another thing which has to be taken into account. This diagram and also these quantities refer to stochastic failures. If I remember the type of failures I had to deal with during my active time, the majority were not the results of stochastic failures. The majority were results of design problems or setting problems. And that are not stochastic things. For instance, if you have a protection concept where somebody did a wrong design because a signal was misinterpreted, or we even have a software bug in the protection relay, it's not a stochastic thing. It's always there and it shows up in a dedicated situation. Or if you have a setting problem, this problem is always there, but it becomes only visible if you have a fault at a location where this setting problem results in wrong reaction. And this has to be taken into account. Before we look into that a little bit deeper, I just want to introduce two terms in this context, unwanted trip and missing trip, that are two terms which are often used in protection, that are the terms dependability or security. Dependability addresses, can we depend on the relay that it will trip if there is a fault in the zone? That means the dependability addresses the risk of a missing trip. On the other hand, the security addresses the risk of an unwanted operation. That means if we want to increase the security of a protection scheme, we want to reduce the risk of an unwanted trip on a fault outside the protected zone. And these two issues have to be balanced. If we, for instance, increase the dependability, we may decrease the security. That means we must make up our mind what is the proper balance for that. So that were some theoretical considerations. And now the question is, what can we as protection engineers do to improve the reliability with a limited budget? Think of, we always have these economical constraints, and it's important if we say we want to improve something, where to do the investment. You can, for instance, compare that with your house. You want to make your house burglar proof. And then there are people who invest a lot of money into the front door, make a very safe front doors that no burglar is able to come in. But he doesn't look at the back door he has in the house. And then he comes in through the back door. It's very easy to come in. And in this simple example, you see it was a wrong investment to invest all the money into the front door. You should have taken half of the money and invested into the back door. And we have a little bit a similar situation in protection. We have to look, where do problems come from and where should we do something to improve the situation. And there we have to look at these three classes of problems: stochastic failures, design problems, and setting problems. What can we do to reduce the rate of stochastic failures? We need higher reliability of devices. That is a thing of a manufacturer. And we invested really a lot of brain to design the devices in a way that the outage rate is pretty low. You know, our technology doesn't accept fans. That means we have cases which has no ventilation, and electronic components produce a lot of heat. We must get the heat out of the box, and that is a design question. You must think about how to arrange the components inside the box that you don't get hot spots, and especially you don't want hot spots near electrolytic capacitors because they are pretty much sensitive on that. That means reliability of devices on one hand is first of all, a manufacturer issue, but not only, you will see later on. Also, the selection of components used to build protection relay is such a thing. And with all the measures, state-of-the-art design, you end up on a certain reliability level. Not at 100%. You will never reach the 100%. Then, and that is now the question of the user of protection relays, we typically have redundancy. That means we must design our protection concept in a way that if one device fails for whatever reason, because the relay is out of order, the circuit breaker doesn't work, the wiring is damaged or whatever, if one relay doesn't work, there must be something else. There must be a backup for that. And that is an important design criteria for the protection concept. You always have to think, if this protection relay fails, who is going to do the job? But there are also some other measures to reduce the failure rate. One thing is better maintenance. Are your substations regularly maintained? But also, what do you do as maintenance? The protection relay itself is basically maintenance free. You may have to look, for instance, at the wiring. Is there anything wrong in the wiring? Is the insulation of the wires okay, or whatever? Another thing is the environmental conditions. Where are the relays installed? And I can tell you, I've seen relays where you couldn't see any colors on the components. So they were installed in a dusty area, or you even may have corrosive gases there. And of course, if you have these conditions, the relay will work, but after some time, you will have an increased failure rate. And you have to take that into account, or you have to think about, does it make sense to install the relays in a better place? And the last thing I mentioned here is the question, how long do you keep relays in operation? Do you preventive replacement with a certain concept if the relays reach a certain age, or do you just wait until they fails? Also there, different concepts are in work. All these things refer mainly to stochastic failures. Then we have the design problems, and that is a thing which affects the manufacturers of relays, but also the users. The manufacturers have to look at their development processes, design, also testing. Are the processes okay? Is the experience and skill level okay? Do we have proper test procedures? But that also refers to those people who build the protections or who design the protection schemes and also do the commissioning. Also there you can make faults. And also there, these mistakes which are done, and also there nobody will work without mistakes. Mistakes happen. There the question is, do we have processes to detect mistakes? Do we have sufficient skill level for the people working with that, and so on. And the same refers to setting. Also there, we must have a look, is the responsibility clear? I found many cases where we had to analyze protection maloperations, and it was not clear who had the responsibility to calculate the protection settings. To calculate the protection settings, you need certain knowledge about the network. You cannot tell the commissioning guy, yeah, just you know the relay, please do the settings. You need some knowledge about the network, sometimes a bit more, sometimes a bit less, but you need some knowledge about the network, and it must be clear who has the responsibility. And also there, it may be necessary, especially if you have fluctuation of staff in this area, you must think about, could this area be the back door where the problem comes in? No? You invest a lot of money into building redundancy, but on the other hand, the setting calculations are wrong. And another issue is with settings. You calculate the settings today based on the network situation you have today. Then your system may grow or may change, because you have new renewables installed there, the load grows and whatever. And that means after some time, the settings may no longer be valid. You may have to adapt the settings. Also, this procedure must be looked at carefully. So you see, there are different components you have to have a look at if you want to improve the reliability of the system. It is not only the MTBF of the protection relay, and that is the message I want to give with this chapter. And think about this example with front door and back door. I think that's a good equivalent in this case to motivate investment at the right point. So that is the end of the reliability chapter, and after that we will do the part 2 of building a protection scheme. So after these considerations about reliability, I would like to do the remaining part of our section, building a protection scheme. That means look at the required redundancy and backup level. And the leading idea in this context is always what happens if one protection relay doesn't work as desired. That can mean you have a failure of a protection relay, of wiring, of the circuit breaker, and whatever. Then the protection scheme must be designed in a way that another relay takes over this responsibility. And there are different concepts to do that. Let's look at this simple installation. We have a line with an indicated short circuit. We have a protection on both ends, and we have different options to do a backup or a redundancy in this context. And the simplest thing is you just duplicate the protection. That means instead of installing one protection on both sides, you install two protections on both sides. And now the first question in this context is, what are you going to do with the trip signals? Can both trip individually? That means, will the breaker trip if one of these two trip? Or do you make a 2 out of 2 logic? That means you will only trip the breaker if both give a trip signal. That is again this discussion about dependability and security. But state of the art in this context is both relays or both protection schemes are independent. That means both relays can trip. That means you can even take one of the two protections temporarily out of service for maintenance or some changes. Then the other one will remain in operation, and if there is a short circuit, it will trip. This can be two identical relays, for instance, two distance relays. Some people say, I don't trust a manufacturer, I take two manufacturers. In the early days, people said, I have one digital relay and one old-fashioned one, electronic or electromechanic even. But nowadays, we have more and more applications where we have communication available, and that gives us the possibility to install, for instance, a distance relay and a line differential relay in parallel. So that is the concept that's called main 1, main 2 concept. You can imagine that is the biggest investment, and you will only do that normally in transmission systems. You will normally not do that in a distribution system. I would just like to add one command in this context. We also offer relays where you have a distance relay and a line differential relay in one box. that gives also some redundancy, but that is not what is required here, because if distance and line differential are in one box, if this box fails, there's nothing left. That means if you have a main 1 and main 2 concept, you need really two separate relays. But nevertheless, you can say, okay, one of these two relays is, for instance, a relay which has a line differential and a distance on board. And for instance, if the line differential goes out of operation because you have a communication problem, then it activates automatically the distance protection. So you have different options there. Duplication of protection, main 1 and main 2. And that, of course, gives the maximum on redundancy. Even if one relay fails, you still have a full selective fast tripping. But you also have the maximum on investment. The next step would be a bit simpler. Let's take the same example here, the line. And let's now assume you have a line differential protection here. And the line differential protection, it needs communication between two ends. And if this communication fails, the line differential is dead. And for that reason, it makes, for instance, sense to install in parallel to the line differential protection an overcurrent protection as a backup. There you also have two devices, but it's a much simpler thing as having two full-blown distance protection schemes there. That is a thing which you could, for instance, find typically in a distribution system. That is called main protection with local backup. That means you have one backup device installed locally. And in case now the differential protection fails, you have to trip this fault with overcurrent protection. And we will see overcurrent protection tends to have a bit longer tripping times. You may also have some selectivity issues here. So the quality of the protection is a bit lower in case of a backup situation. And the last thing I would like to mention here is the so-called remote backup. Imagine you again have the same situation, a line with two distance relays or two overcurrent relays on both sides. And then we can make a tricky design, and that really saves money because you don't have to install separate devices for backup. You can parameterize, or you can design the protection concept of the previous line or of the next line in a way that it also looks into your line. That means in case the center protection relay fails and you have a fault on that line, then the left side relay will also see that fault. We'll see, I see a fault, but it's not on my line. I will not, first of all, not react fast on it. But then if the fault is still there after some time, it will say, okay, this looks like a backup case now. Normally, the fault should be cleared in a pretty short time. If the fault is not cleared, it looks like a backup, I will trip. That means at least the fault is cleared. That's the good thing. The bad thing is the tripping in this backup case is done a bit slower because you have to wait. And it's also not full selectivity because you lose not only the line with the fault, you lose also, in this case, the line on the left-hand side. But the fault is cleared. And that is a thing you find all over the different voltage levels in systems where you do protection with overcurrent and distance relays. We always use this concept of remote backup. It gives you a backup without installing additional relays, but you must have in mind, in case of a backup, you will have a delayed tripping and you will also have reduced selectivity. That means you take into account some deficits concerning trip time and selectivity. Here you see again the comparison. Duplication means two independent systems operate in parallel, and the other one was main and backup protection, and there we accept some limitations in speed and selectivity in case of the backup situation. And also here you can again see that is the economic constraints. Economic constraints bring you in a situation that you accept additional risk. Well, you have reduced selectivity, longer tripping times to save some money. But it's state of the art to do that. And important rule behind that, in all cases you must think about which device does the backup in case of a missing operation. That's always the idea behind that. So now finally I would like to look into a few examples just to show how these protection concepts look like. And before we do that, I would like to show this table. The problem if you draw these overview diagrams about protection concepts, you would normally have to write a lot of long words, distance protection, overcurrent protection, synchro check and whatever. And that makes the diagram a bit confusing. And for that reason, we often use these so-called ANSI numbers for protection function. The idea is very simple. You list all protection functions we have and you assign a number to it. And protection engineers normally know that. That means if you wake up a protection engineer at night at 3 o'clock and ask him what is 21, he will tell you distance protection. Very clear. So that's at least the main numbers are known and they make these diagrams a bit easier. So you see here a lot of numbers. A little bit the disadvantage is that these concepts are sometimes not really unique. They are different dialects of these numbers, but I think they are useful. You sometimes find the letter N behind a number, then it's a function which reacts on earth fault or which is tuned for earth faults. We also have NS, the lowercase s means sensitive. And we also have some functions where we don't have a number, like you see there the PMU, phasor measurement unit, the synchrophase measurement, or the FL fault locator, where we measure the distance to the faults. So that are some newer developments where people didn't assign the number. So these numbers are often used in the diagrams. And now let's have a look at the example. The first example here is a simple, or it's not that simple, it's a medium voltage feeder protection. So you see on the left side, on the top, the two bus bars. And then down you have the feeder. You have two isolators where you can connect the feeder to one of the two bus bars or even to both bus bars. Then you have the circuit breaker, you have the line side isolator, then you have the current transformer, the line side voltage transformer, and in this case we also have a voltage transformer on the bus bar, which we, for instance, need to have a synchro check functionality. So, and all these things are connected to the device. Now remember, the first step is we must think about what is the main protection function. And in this case, we have a medium voltage feeder protection. So typically you apply overcurrent protection there. You see here the three functions we are going to use in this case, the 50 and the 51. Depends on whether we use definite time or inverse time. Remember, definite time overcurrent is the overcurrent with the stepped characteristic. Inverse time is the relay with the time-dependent trip delay. And in this case, we also have a directional overcurrent protection. We will hear in the following selectivity chapter a bit more about what is the benefit of installing a directional overcurrent protection. So that is the main protection, short circuit protection. Then in this case, you see we have added some other blocks here. In this case, we have 5 additional functions. First of all is a switch onto fault function. That is also a functionality I didn't explain up to now. What does switch onto fault mean? As I already described, you often have some delays. You need in overcurrent protection delays to get selectivity. That means especially at the beginning of the feeders you have long delay times. And this particular function addresses the situation where you have the feeder, the whole feeder out of operation, and now you reconnect the feeder and somebody forgot to remove an earthing switch or whatever. That means you have still earthing in the feeder, you close the breaker, that means you connect the part of the system where still earthing in there to the bus bar with nominal voltage. And that means in the moment where you close the breaker, you directly see a fault. And for this particular situation, we use a so-called switch onto fault function. That means the protection relay knows I'm now closing the breaker, and if at the same moment a fault occurs, it knows it doesn't make any sense to activate delay time to wait for 600 milliseconds. The fault, the short circuit it sees is a result of closing the breaker and it directly opens. That means this switch onto fault function, soft sounds a little bit strange, the switch onto fault function gives you a fast tripping in this particular situation. FL is the fault locator, 25 is the synchro check, where we assume it is used here. It requires 2 voltage transformers, one on the line side and one on the bus bar side. We have a 50 BF, means breaker failure, and in this case we also have auto reclosing function because we assume it is an overhead line. That means you find somewhere here also the 79, which is the number for auto reclosing. And then in this case we also have some control logic included there. That means you see here additional some control functions, some logic, maybe interlocking logic for the control of the breaker. So this would be an example for a medium voltage feeder. If we come to high voltage, I can show this example. We have here again a very simple feeder. We have a bus bar. In this case, we have not that much control available in the relay. That means we run the relay as a pure protection and assume that the control function is somehow in a separate device. That means we have connected here only the circuit breaker. We have a current transformer. We have a line side voltage transformer, and we also have a bus side voltage transformer. On the right hand side, I again list the protection functions of these 3 steps. The main protection function in this case, it's a transmission line, is the 21. It's a distance protection. That means you see the 21 hidden, although it's the main function, it's hidden amongst these other blocks. And then in addition to the 21, we have a number of additional functions. We have a backup overcurrent. What does backup mean in this case? In distance protection, you have the situation that the distance function needs the voltage measurement. Now, because we have to calculate the impedance, we have to divide the voltage by the current to calculate the impedance. The voltage measurement inputs are connected to a voltage transformer, in this case the line side voltage transformer, and now you assume that for any reason you have a short circuit in these wiring there between the relay and the voltage transformer. You make a short circuit there for whatever reason, and that means suddenly the relay loses the voltage because you have an MCB there and that will trip the voltage input, and then you suddenly see zero voltage. And now the situation is zero voltage means to calculate the impedance, you divide zero by a current, and the result is zero. That means you measure the impedance zero, and that would trip. And it doesn't make sense to trip because we have a short circuit, but not on the line. It's a short circuit just in the wiring. And for that reason, protection relays have typically a detection function which detects this situation. That means it detects a suddenly failing measuring voltage and then automatically blocks the distance protection. If you wouldn't do anything, the distance protection would trip in advance. That means this must be a very fast detection function, and also it must not overreact. That is called backup overcurrent protection. That means if this situation occurs, the distance protection is blocked. As a backup, we run the whole system only with overcurrent protection. If we don't like that, we take the main 1, main 2 concept. If we don't want to do the investment, we must accept limitations in tripping time and selectivity by using backup overcurrent. Then we have a ground fault protection here. The reason there is, I mentioned it already, we have normally in transmission, or we have always in transmission systems where the star points are grounded. That means distance protection will react on phase to ground faults, but it has limitations in sensitivity. We will see that in the following videos. We can only detect faults up to a certain fault resistance, and if we want to be more sensitive, we must have special functions which are tuned to detect these ground faults. And in this case, it is a 67N, that is an overcurrent, directional overcurrent, which is tuned for ground fault. Then you also see switch onto fault. It's called here a little bit different. 50 HS, high speed. We have under voltage, over voltage, frequency, and we also have here the power swing detection and tripping. Remember, the power swing function has 2 possibilities. It can either be used to detect the power swing and block the distance protection, that it doesn't make wrong trips, or we can use the power swing function for dedicated tripping. And then as additional functions, we have the fault locator, we have the synchro check, breaker failure protection, auto reclosing, and teleprotection. You see here the teleprotection is a function which is nearly always or very often used with distance protection, but it also requires communication to the other end. And for that reason, you see here on the left bottom, you see communication links where the teleprotection function 85 communicates with the relay on the other end of the line. So that was an example for transmission line protection, and the last example refers to transformer protection. For bigger transformer, standard main protection is the transformer differential protection. It is called here on the right-hand side 87T. 87 is the standard number for differential protection, and the T means we have here a differential protection in use for a transformer. And then we have two additional functions. The 49 is the overload protection, which is a standard thing for a transformer. Avoids thermal overloads, avoids heating up of the transformer. In this case, just based on the current measurement. Otherwise, we would also need a temperature sensor in the transformer or several temperature sensors in the transformer. And we have 50 and 51, which is a backup. And also here in this case, as we have the main short circuit protection is done with the 87T, the faults in the transformer are detected with 87 with the differential. The overcurrent here is mainly used as a remote backup for the following lines. I didn't explicitly mention this thing in the previous two examples. There we had an overcurrent and a distance example, and in these cases you automatically have the backup in terms of a remote backup. That means you actually don't really have to think about backup because it's automatically there. You only have to think about backup when you calculate the settings. Here in the differential protection, the differential protection itself is not able to do a remote backup. Differential protection only looks at its own device, in this case the transformer, and whatever happens outside, it will not react on that. That means if we want to have a backup protection in a transformer protection relay, which reacts on this backup case, if there is a fault on the next line where the protection fails, we must install separate functions for that, and this is in this case the backup overcurrent, in this case 50 and the 51. This was the last example, so we have now a few ideas how we compile a protection scheme, what ideas are required to set up a protection scheme. And in the next series of videos, I will explain a bit how do we achieve selectivities by selecting proper settings. In the devices, we will discuss that for overcurrent protection, and separately, that's a bit a longer discussion, also for distance protection.
Thank you, Siegfried. That has been an interesting session with insights into the basics of protection technology. Dear auditorium, thanks a lot for your questions. We will answer these in the Q&A session on 21st of June. If questions come into your mind later, or you would like to go for more details, please visit our training platform at Siemens Power Academy. I'm sure you will find the right information and training. The access to the recording and the slides will be sent to all participants. Thank you very much for your active participation. It was a pleasure for me to guide you through this third session on basics of protection technology. In this session you learned how to build a protection scheme, the challenges creating reliability. I'm looking forward to meeting you soon in the first session of Selectivity in Line Protection on June 11, which is focusing on how selectivity works in overcurrent protection and how selectivity works in directional overcurrent protection. Stay safe and sound, take care, and goodbye.